I'm pleased to be joined today by Dr. Mark Ho. He's a cognitive scientist and postdoctoral research fellow at Princeton University. His research focuses on computational models of human planning, social cognition, and mental representation. Mark, welcome to the Nature Nurture podcast.
Thanks so much for having me.
Thank you. So I think we could kick things off talking about your recent Nature paper. This is how I discovered you, as I mentioned, as a cog sci person. It was so cool to me. So you're looking at mental representations and how people plan, and I'll let you take it from there and give a better summary than I can.
Yeah, totally. So the paper, it's called People Construct Simplified Mental Representations to Plan. And the motivation for the paper is really thinking about this cognitive process that we call planning, where you kind of have a model of the world and you're kind of thinking about the world and kind of choosing what to do based on that model, maybe doing some kind of simulation. And a lot of the work on planning, it's really based on this old set of ideas based around this idea of heuristic search, where you kind of start with a model of the world and then you simulate in that model and kind of generate candidate actions, simulate possible outcomes, and then choose the one that looks the best. The kind of goal of the current paper was to kind of analyze the model formation process, which is kind of a topic that hasn't really been focused on too much, even though it is one of the kind of big questions that kind of people who developed these ideas about heuristic search, Alan Newell and Herb Simon back in the 70s, this question of where does the kind of problem representation, the task representation, they called it like the problem space. These days we would call it like the Markov decision process or something like that. Where does that representation come from in the first place? And the idea of our paper was to kind of think about it from a kind of bounded rationality perspective, and kind of understand how the kind of construction of the selection of a particular model to solve a problem is really motivated in large part because we have limited cognitive resources. And so a lot of these ideas are kind of floating around out there and kind of out there in various forms, but the kind of goal of the paper was to kind of bring them all together, create like kind of coherent model out of that, and then really test that using psych experiments.
So up until this point, most of the focus is like you see a question or a problem and you construct a mental representation of that, and then most of the focus is on like, what's the solution and how do we use our cognitive effort to lead us to a solution. But we've taken for granted that you need the mental representation before you can start thinking about that.
Yeah, so definitely from like a computational perspective, that's been the working assumption that we kind of have a model, the experimenter assumes a model and gives that to the participant, and the participant uses that model to do some kind of search over. That's how people especially people who are computationally modeling planning, have tended to think about things. That said, there's a lot of work kind of partially, it's been around a long time before kind of Simon and Newell invented these ideas, and also a lot of work kind of in reaction to these original models, kind of studying this exact question of how the role of the representation. So there's a lot of classic work on like analogical generalization. So if you kind of solve one task that has a certain structure, can you generalize the kind of abstract structure to a new task? That's a type of representational transfer. And then work on like insight problem solving. So like Dunker's candle problem. I don't know if you're familiar with that idea. It's kind of this classic experiment from the 40s that they brought people into the lab and they gave them a box of tacks, a candle, and then a book of matches. And they were told that they needed to light the candle and have it kind of pinned against the wall somehow or on the wall somehow. And when you give this to people, they have a lot of trouble solving it. They try things like melting the candle onto the wall or kind of tacking the candle onto the wall, things like that. But what you're supposed to do is empty out the box of tacks, put the candle in the box, and then tack the box to the wall, and then put the candle in the box and then light it. And so, yeah, so it's kind of like one of these like trick question type things or lateral thinking problems. And it's often described as a kind of representational impasse. So you're kind of stuck. So when you're first presented with the problem in this way, with the text in the box, you conceptualize the box as a container for the text, and you're having trouble. And so when you're asked to then somehow get the candle on the wall, you continue conceptualizing the box as a container. And so that blocks you from thinking of it as a surface or a shelf that you can put the candle in.
Right. What's that term called when it's like you can think of multiple uses beyond a traditional use, like not using just a hammer as a hammer, but using it as like
like
a hammer, actually,
like a doorstop or something.
Yeah.
So the term is functional fixedness. So right, there's all this like kind of classic work from like the 40s and so on functional fixedness. People did all this other work in the 60s, 70s, and 80s on related ideas, and these ideas all had to do with the representation of the problem, and they were kind of presented as alternatives, as kind of evidence that the kind of heuristic search story, the idea that we have a model and that we're just kind of searching through it, kind of chugging through a set of possible sequences in it. They really challenge that idea, and but what's been lacking is a way to kind of synthesize those ideas and kind of have it just a single unified kind of computational theory. And so our paper was really trying to kind of like take a step in that direction and think, okay, how can we incorporate this idea of the representation into these planning models, and then also kind of give a rationale for why certain representations appear and not others.
Yeah, I want to go off on a tangent for a moment.
So
it seems like functional fixedness is a good example of something that requires creativity, which is I guess like true general intelligence. So it seems like computational modeling works best when you have sort of a set problem, like there's going to be a most efficient answer, but then once you start getting into needing novel creative solutions, it becomes more difficult to computationally model. Is that right?
Yeah, I think that's right. I mean, I think part of the problem is that when you're trying to come up with creative solutions, like interesting cases where there are creative solutions involve like a vast space of possible solutions. And so just kind of modeling very large spaces is hard. It's something that a lot of people are trying to work on now and kind of push the envelope on. But that is a big challenge, I think, with understanding creativity, computationally at least. But I do think that there are, if you can come up with like kind of well-defined enough tasks that have non-trivial solutions, but also kind of force the participant to like think differently, they can be, if they're well-defined enough, you can still model it. And so like these, so for example, like anagram tasks, where you give someone like a bunch of shuffled letters and they need to figure out what the word is. I mean, they're like, you can think of that as a kind of creative problem solving task. There is a single right answer. It's not like, paint a totally new picture or something like that, but it does require kind of like thinking flexibly and kind of rearranging kind of your conceptualization of the letters and stuff. And so, but I do think, I don't think it's totally out of the realm of computational modeling to study things like creativity, but it is definitely a challenge.
You know how sometimes there are like multiple solutions, but there's going to be like a local optima, and then maybe there's like a better global optimum. So like with a neural network, for example, if it's using something like gradient descent, it can fall into this slump thinking that there's a best answer, but you need to introduce additional noise so it gets creative enough to try new solutions. Like one example I can think of is it was Google's DeepMind AI, and it was training a humanoid figure to walk. And they measured progress by like how far it can go distance-wise. And for the first several thousand iterations, it learned to jump and essentially just launch itself, and it would fall, but then, then it would spread its arms. So the distance would be measured by where the arm landed. So it was doing pretty well. It got like 6 feet, but it didn't learn to walk until it kept trying for like several million more iterations until it learned, oh, launching myself and then not getting back up isn't actually the best solution here.
Right. Yeah. I'm not familiar with that particular experiment, but yeah, there's a lot of interesting work kind of like with evolutionary algorithms and stuff, trying to figure out how to get how agents give it a kind of general loss function or fitness function, and then kind of see what happens. That I think, yes, I guess like the field that comes to mind is like, it's called like open-endedness, like research on open-endedness. They're interested in this, like these kinds of questions, like how do we design, how can we kind of get an algorithm, write algorithms that can come up with creative solutions to things. And yeah, one thing that's interesting is that one of the big challenges is kind of the space over which you're doing the search, the search for solutions. And so if you're searching in like kind of at a very low level, so for example, in like the kind of walking like creatures examples, like if you're searching at a very low level, you can easily get stuck in local minima. But if you kind of have a higher level abstractions of like having legs, like 2 legs, 3 legs, 4 legs, things like that, then you can get more interesting. You can search the space more systematically and get more kind of like jumps in like solution space.
Yeah, that's really cool how that happens. Okay, so back to the paper to try and set the visual stage for this. So one example you gave is, let's say you're trying to navigate and you could have like a satellite picture of a fully detailed map, and that would require a lot of information to have that full map with all the details. Or if you're driving in a car, you could have a bare minimum map that just shows the roads, and presumably it would take less cognitive effort to memorize the road map and not have to memorize any of the details, like where the trees are or the mailboxes or things like that. So one part of the problem is how to navigate, what the optimal path is along the roads. But then another part of the problem is like, what's the simplest map I can make that will still work?
Right, exactly.
Right. Okay, so it seems like the goal of this paper is not to really care about the path itself, but more on the focus more on how do we construct our mental maps.
Right, totally. Yeah, so how do we construct our mental maps depending on what our current goals are, whether we're in a car, whether we're on a bike. But what's interesting about the construction of the models is that we can't totally ignore the influence of the plan or the policy that we're going to use the map for. What was kind of a big insight for us in developing this model was that the way in which the model is going to be used for constructing a plan, and this kind of back and forth, this kind of codependence between the plan that you need to compute and the model that you're going to use to compute that, that's really important. And so like, it's not just that you're kind of coming up with a map, because in the limit, you could just come up with a map that only includes the road that you're going to be taking and doesn't include any other roads. But that's not going to be very useful in like other contexts. And you're not going to kind of come up with a totally new map for every single task, every single driving task you're going to use. You're going to kind of come up with maps that are kind of usable across problems, usable across clusters of problems. And so that's kind of the idea here, that we kind of have a set of kind of simpler representations that at planning time, we combine those, plan with that, and then can act effectively. And so it kind of facilitates a more flexible kind of generalization as well.
So this would be speculating way beyond the paper, but when you're driving, you know how sometimes, especially if it's late at night, maybe you're tired, you kind of go on autopilot and you don't have to register. You don't have to consciously be behind the wheel the entire time, especially if it's green lights all the way through and you're staying in one lane, or if you're on a highway.
Right.
And if there's a red light, or especially if there's something unexpected, like maybe you catch a pedestrian out of the corner of your eye or something, and it looks like they're about to walk onto the street, then you suddenly have to kick into full attention mode again. So do you think that you're dynamically updating these maps? Like you can use a simple 1 second, and then a second later, new details come in, and you have to like dynamically start using a more complex map?
Yeah, absolutely. I think so. Yeah, it's not, the paper really focused on this very controlled situation where there's kind of a single type of problem and it's changing in a certain way. I think, yeah, in general, we're kind of constantly, shifting between simpler maps, more complicated maps, like automatized behavior. So if you're driving down a road that you've driven down a million times, all you need to know is whether there's a green light in front of you. And so maybe you're not even doing really planning per se. You're not actually modeling the world. You're just kind of responding to the green light. But then when something novel happens, or like, the road is blocked and you have to figure out, take a new route, then you have to start planning. And so, yeah, the way we're thinking about planning is totally consistent with these kinds of other types of decision-making mechanisms, more automatized things. But then also your point about kind of dynamically updating your map. That's something that, yeah, I definitely think people are doing. We started to model that a little bit in the paper to kind of capture some of the variability in the data that the kind of static, simpler model didn't capture. But yeah, I mean, I think as we're kind of going through the world, we are forming representations differently. So one example that I like to use is, let's say you're planning to go to take a flight from the airport at the airport, and you're at home and you're packing your bag. The way you're kind of representing the airport and thinking about the airport while you're packing your bag is very different than once you're at the airport. And you kind of have to figure out, oh, how am I going to get to my gate? How am I going to catch the flight on time? Is there a bathroom on the way? Stuff like that. But somehow there is this correspondence between the abstract representation, the much more abstract representation of the airport when you're at home, and the more fine-grained, filled out version once you're at the airport. And we can think of that as a kind of dynamic construal process. In fact, like some inspiration for this work came from thinking about things like construal level theory, which is all about kind of how do we perceive things at different levels of abstraction. This kind of work in social psychology, thinking about how do we perceive the same object at different levels of abstraction, depending on how temporally distant or psychologically distant that thing is.
The switching between those multiple maps, one more detailed, one more sort of abstract and simple or far away, seems much more obvious. But then, do we know anything about how that happens? So two competing hypotheses might be something like, in one case, you have both of these maps like latent in memory, and then you just switch to accessing one or the other. And then another version might say something like, we don't store the maps at all. We're generating them on the spot every single time. And it seems like there's pros and cons to each of those, because generating new maps every time, it sounds harder, but then also you'd be saving the energy of like having to store things in the background.
Yeah, totally. I mean, yeah, this isn't, I don't know if this is a non-answer, but I think it's both. I think we're definitely doing a little bit of both in everyday problem solving. Like, for very familiar situations, we might have a standard way of kind of switching between a finer grained, more coarse grained representation of a thing. And for maybe when we're solving novel problems that are more complicated, we have to kind of construct new abstractions that allow us to deal with them. So this is something, I'm trying to think of a good example, but this is something that like computer programmers have to do a lot, where they have to kind of, to manage large blocks of code, large code bases, they need to break it up into more manageable abstractions. Some of that is just like, they've solved a problem like this before. They know how to like form the right abstraction. They're just drawing on an old way of kind of coming up with an abstraction. Other times it involves kind of creatively coming up with a new abstraction.
Yeah, so the coding example is pretty cool here, because sometimes you might write a function specifically for one purpose, and the task comes up at some point in your code and you call the function, and it's kind of a standalone thing the entire time, and it's standalone naturally. And then other times you might have a whole bunch of code and it's just exhausting to keep track of, and you artificially add these chunks and then you label the chunks. So I'm guessing again it's both, but do you have anything to say about how we organize things like sort of naturally based on function versus like going out of our way to sort things into chunks?
Yeah, I mean, I think yeah, there's definitely a little bit of both happening. I mean, one role of function is to kind of capture like a repeated computation. So like if you're, you know, doubling numbers a lot, or like concatenating lists, maybe you want to have that as like a repeated function. Yeah, but I think it's, yeah. And so there's work thinking about that kind of like compression, like the compression perspective gives you the function stuff, but the, this idea that you kind of have a large block of code and like intentionally break it up, not so that you can reuse pieces, but just so that you can like understand the high level structure. That's, yeah, that's interesting. And I think there's people have thought less about kind of that, the ergonomics of that. But I definitely think that is something that happens. Like we just, you know, we have a limited capacity to represent a thing. And so we want to kind of break it up hierarchically for its own sake, so that we can kind of comprehend the whole thing. I mean, it's like outlining a paper or something. Like a well-constructed paper has that. Yeah.
You play video games, Mark?
Yeah, a little, not as much as I want to, but
there's two ways I could get at the same idea. One would be a video game. So you could say like, you know, sometimes games, rather than having to draw like thousands of trees and put them in the game, there's like this procedural generation. So it's like, there's sort of this platonic form of a tree, and then you just add noise and variation, and you can create thousands using like a single function. And then I mentioned platonic, so the more philosophical idea would be like, you have this sort of schema of what a tree generally looks like. And then especially in like cognitive development, there's a lot of work here on like how children represent basic schemes, whether it's tree or dog or cat, or like these very general ideas, even though there's not such a thing as like the dog. It's just they're sort of all sharing in this characteristic of being a dog or a tree or a cat or whatever.
Right. Yeah. Interesting. I guess. So do you see those two as kind of getting at a similar thing or opposing?
Well, I'm wondering if the way that children create those sort of cognitive representations is similar to how it's done in procedural representation, where it's like I'm wondering if it's a similar algorithm to what happens in video games, where it's like you have this sort of basic idea of what the image looks like, and then you're adding variability. If we do that in our minds, but then it would be sort of in reverse order. So rather than starting with the ideal image and then adding the variability post hoc to create something new, it would be more like we perceive that variability and then remove it, and then we end up with whatever that basic schema is.
Right. Yeah, I mean, like, yeah, it's interesting. I do think, yeah, I mean, this isn't my area of expertise at all, but I do think that like I think so, yes, a number of researchers, I'm thinking of like Josh Tenenbaum and Tom Griffiths have kind of proposed this idea that, you know, maybe the things that like game engines are doing that like people who design, like game designers have come up with, they have to deal with the kind of computational demands of simulating worlds. And so they've come up with all these neat algorithms that do things like you're describing, like kind of have like a canonical tree and then kind of create a bunch of variations on that. And that, yeah, maybe that could be like a model of how humans, infants, like children are kind of how they build up their own mental model. Because, you know, the mind is also subject to computational limitations and kind of needs to make these shortcuts. So yeah, I do think it's a plausible theory. I don't know. Yeah, I can't say it. I don't know which is more plausible at the moment, but
and my favorite part about this podcast is being able to speculate on ideas wildly outside of my own area of expertise. But so, and a lot of the things we're talking about right now are very visual, which is somewhat difficult to translate into podcast format. But I'll link the paper we've been talking about in the description, because I want to applaud you on the study design and how you presented all the visual cues, because I thought it was very clever and elegant. Like especially the the idea of, saying, so there were these obstacles in the maps that you presented, and you tried to guess whether people remembered the obstacle or not. And rather than just doing that, you added a fake one and said, it was one of these, which one is it? I thought that was a great way of getting at their true representation.
Yeah, we had a lot of fun kind of coming up with some of these experiments. We kind of went through this review process where we were asked like, oh, couldn't this be confounded with perception or just executing or something like that. And so we came up with versions of the test. So we were really trying to think, okay, how can we control for these things? And it was a lot of fun to really think, okay, how can we show that like this is what's happening? And so we ran these versions of the study where people were given the exact same stimulus but had to interact with it differently, kind of manipulating the kind of frame that people are approaching it with, and showing that attention was different and not as well predicted by our model. So yeah, and a lot of that, I tend to be a very visual thinker, and like if you've seen my other papers, they're almost all like kind of grid world. A lot of them are like very grid worldy, like 2D kind of visual things going on. But I do think it's a good way to kind of like build up the intuition. People understand it it's like easy to kind of see how, okay, we, kind of layering on more complex pieces of the task and so on, how that all works.
Yeah, this would be a great place to jump off to some of your other papers. So obviously you're a postdoc now, so you've been doing research for at least like 7 years, right?
Yep.
Yeah, so
a little bit more. Yeah.
Major themes that you'd like to talk about? We could talk about other specific papers or just general themes of your research or anything like that.
Yeah, we can start general. I've been thinking a lot about kind of how all the projects I've worked on are connected to one another. I think other than kind of similarity in paradigm, I think a lot of them are trying to deal with this question of intentionality, I guess, if you want to describe it more philosophically, like intentionality and like planning, and kind of thinking about, what does it mean to be like a goal-directed agent in the world? And how can we understand the computations that are going on there? And so a lot of my early work was on kind of thinking about teaching, kind of thinking about intentional action in a more kind of social interactive context, and thinking about, how do we like teaching as an intentional activity that humans engage in. And that seems to be like, to a certain extent, like distinctively human, and kind of like somehow we have this work where we have people kind of intentionally trying to communicate with another person, how they, how like a certain like task works, or like kind of what the values are of certain objects in like a grid world. And and so we model that as a kind of intentional teaching, a kind of, you have a model of the other person, and how they are reacting to your actions, and you are trying to kind of intentionally move their beliefs around to get them to believe the thing that is true, that you're kind of encouraged to teach them. And so
does intentionality require this subjective human component, or is it just based on the idea of agent and task? So like, for example, could you say that a chess bot has intentionality, and that its intentionality is to win the game?
Yeah, that's a good question. We recently had a workshop on that at RLDM, and I organized it with David Abel and Anna Haratunian. And the theme of the workshop was, is reinforcement learning a good model of agency? And a kind of thing we were trying to get at there was like, what are the kind of necessary conditions for an agent? Is a chess bot an agent? Is a thermostat an agent? The thermostat is, it perceives the heat, the temperature of the world. You could argue that it perceives the temperature and then reacts to it and kind of keeps it, has a goal of kind of keeping the temperature at a certain level. So I don't have an answer to like what makes an agent and whether a chess bot is an agent. I think like, certainly agency in like the strong sense requires something like model-based planning. I would say that. I don't know if it's sufficient, but kind of the ability to kind of think about, like, have a representation of the world or the domain, and kind of simulate what you're going to do in it, and act, and then act based on, you know, what you've simulated, the plan you've created. I see that as at least a necessary condition for considering something an agent. Because if you have, you know, a thermostat is just reacting, even if you had like something that's, you know, reacting in a very sophisticated way, like, you know, like a model-free agent on Atari, like on one of these Atari games like Pong. You know, it's learned to do something very sophisticated, but it's very brittle. It does that one thing. And what a model lets you do is kind of act more flexibly, respond to new situations more flexibly. And I don't know, I do think that this element of flexibility and kind of representing the world is key for this idea of agency, at least this like intuitive notion of agency that we want to get at.
Yeah, have you heard of the, recently there was a Google text bot AI, and one of the Google engineers made headlines for claiming that it achieved sentience. And it seemed like the scientific consensus was, no, it's just an extremely sophisticated language model, and it's like using statistical learning to say things that it seems like humans would likely say in similar circumstances. So it might not be sentient, but it still had me wondering, even if an AI one day did, it would probably be very easy to write it off and say, no, it's just doing what it was designed to do very computationally. So then it's like, I wonder if there's some sort of tipping point at which you get into genuine agency or sentience.
Yeah, I mean, I can't really comment on the sentience question in general. I know that it's kind of a controversial topic.
Tangle sentience from agency, because I tend to view those as fairly coupled. I imagine most people might, but I know that there's a technical difference.
Yeah, right. I think at least, yeah, sentience has this kind of flavor of like consciousness and like subjective experience. Agency maybe does. But yeah, I guess I would say, you know, one question that you can ask in this context with regards to agency is again, what defines agency? What do we need to define agency? Or, you know, what do people think of as, you know, something being an agent? At what point does a person, you know, I mean, like the engineer who was interacting with this bot, they seem to strongly believe in this thing being an agent. What criteria, even implicitly, are they using to evaluate that? And that kind of comes back to like these classic questions about theory of mind, like how do we attribute, you know, intentionality to an agent, or to you know, an artifact or another person or something like that. I will say about the I think it was Lambda was the chatbot. Someone else had a funny thread about how if you ask Lambda to describe itself being a squirrel, it will like go into this long monologue about how it loves being a squirrel, and it just like wishes people understood that it was a squirrel and stuff.
Oh yeah. Very similar to what it was doing when squirrel was replaced by AI.
Exactly, or like sentient being or something like that. So like I do think, you know, these particular systems are definitely able to mimic a lot of things. And, you know, just because it says it is something doesn't necessarily mean we need to believe it. But yeah, I do think, like, you know, this is going to become an issue more and more. Like, at what point do people kind of start treating, you know, these very sophisticated adaptive systems that we've built, our AI systems? At what point are people going to start kind of falling into the trap of kind of thinking of them as intentional agents? It's like having, attributing a theory of mind to them. I'm not sure what to do about that.
Yeah, and back to humans, we don't even seem to attribute full agency to all people. I mean, children are one example where it's like whatever the whole slider scale is from minimal to maximum agency, it seems like we agree that children don't have it, and then adolescents, you start to approach full like adults agency, and then adults presumably have it, but maybe you have like a tumor or something that could mess with your, well, so here's another thing that I think I view as two coupled. I'm not sure if, so agency and free will, is that the same thing?
I don't see them as necessarily the same thing. They are related. They are definitely related though. I think, so free will, yeah, I mean, I guess what do you have in mind with free will? I haven't used the term free will in a long time. So.
Yeah, so this is about to get very philosophical. Although I think that that's the true essence of cog-sci, because we talked about sort of the more computational technical parts, and then now we're getting off the philosophical deep end.
Right.
So, well, I think that the more variables you take into consideration, the more free will goes down. So you could imagine, here's the simplest case. Let's say you're walking and you trip over your shoelace, and you ask the question, did I cause myself to trip, or was like my free will impeded upon? So you could say, if you're defining the shoe as part of you, which when you're walking you probably do, you probably extend your sense of self to include your shoes and your clothes, then you could say, I'd stepped over my own shoelace and I fell according to my own free will. You could also say something like, my body starts and ends at my skin, so the shoe is not part of me, and the shoe actively interfered with my steps and it caused me to fall as something outside of me. So it seems like depending on whether you include or exclude shoe as part of you, the free will can go up or down. And it seems like if the same thing happens with other variables you might consider. So for example, if you're taking into account like your childhood or your environment, all of these other things that might influence behavior, and we can show them to have statistically significant effects. Like, for example, maybe if you were raised in an impoverished area, you're going to have a higher risk for criminal activity or something like that. It's not really causing it in a way that you could say this necessarily leads to this outcome, but when you sort of add the additional variability caused by those outside factors, it seems like you get a more complete picture, but then necessarily the free will of the particular agent goes a bit down as the picture becomes more complete.
Right. Yeah, that's very interesting. It makes me think, so I totally agree that there's a kind of intentional stance that we take towards other people, and that's how we kind of assess whether a thing was freely willed or not, and kind of where do we draw the boundary, because like I guess we have this kind of like idea of like a locus of agency or free will, like somewhere deep in the brain, that like there's like a little guy like pressing buttons or something, a little homunculus. That's like the extreme view, but yeah, depending on like where we draw the line, right, at what causal influences are outside of the agent versus inside the agent, that determines whether we attribute free will to an action.
Yeah. And then at the opposite extreme, you might have like all actions can trace back to the Big Bang, so nothing is free and everything is. I mean, if you start factoring in like quantum randomness, then it gets more complicated, because maybe the universe isn't a deterministic system, but it still seems like the more you zoom out, and then the maximum level of zooming out would be to the Big Bang, then it seems like there's an inverse relationship between how much you're zooming in and what the free will is.
Totally. Yeah. Yeah. And like, so there's this interesting issue in reinforcement learning. It came up in this workshop I mentioned about kind of the agent environment boundary. Like, how do we conceptualize the boundary between the agent and the environment? And so this isn't just a philosophical question, actually. It's actually an engineering question, because when you're designing an RL system, when you're training an RL system, you need to make a choice about where that boundary between the agent and the environment begins. And that kind of determines, it's not as like consequential as, do I have responsibility for any of my choices? But like, even like an Atari, like when you're training like an Atari, like a Q learner to play Atari, there's actually a lot of room between like, oh, do we just feed in the like raw pixels, or do we like transform them in some way and then feed in something that's a little more pre-processed to the agent, and then the agent has to learn on that? Or do we train it on kind of like random kind of like permutations or augmentations of the data or something like that? And so there's actually quite a bit of like, room in terms of like how you set up an agent to learn, an artificial learning agent. Like, what is the action space that it starts learning from versus the one we give it to, we kind of pre-process for it. And so, yeah, I think like, even though, it's a very philosophical question, there are some implications, especially if we're kind of building AI systems that are agent-like. It is.
Yeah, autonomous vehicles are a great example of that. And it does seem like most of the problem is with that sort of object recognition, because it's like, if you could lay it out in a video game-like manner and every object is perfectly mapped out, you could have an AI that's navigating without any accidents, no problem. But it seems like it's much more difficult than we realize to identify something as an object, especially when it's moving. Maybe it's raining, or it's foggy, like all of these different things that make it very difficult to, very difficult for computers to complete CAPTCHAs.
Right. Yeah, I mean, autonomous vehicles are a great example, I think, of the challenges of agency. I mean, so there's a kind of engineering questions, but then, also related to free will, agency, all these things. It's like responsibility. Like, on some level, we care about agency to the extent, for a number of reasons, one of which is, how do we assign things like responsibility when things go wrong? This is a huge issue with any kind of large socio-technical system or a self-driving car.
You worked with Fiery Cushman for a while, is that right?
I did, yeah.
Were you ever on the moral psych side, or were you always focused more on like mental representation?
So I never worked with Fiery on moral psych stuff. I don't think we've definitely not published anything on it, but it's something. Yeah, I mean, it's all kind of in the same stew of ideas. I think, like thinking about intentionality versus habit, thinking about when do we? I mean, all these questions of theory of mind, they are very related to these questions of when do we blame someone for something going wrong.
I did a podcast with him recently. We were talking all about moral agency and punishment, and it was very, very interesting.
Totally. Yeah. So some of the teaching work with Fiery was on punishment and kind of thinking about punishment from this perspective of communication and punishment as so the idea being that, when we think about punishment for like a reinforcement learning agent, or like in like a condition, like classical conditioning or operant conditioning sense, we think of it as like an incentive. But what we found was that people actually think about punishment in much more kind of mentalistic way. So I punish you because I want you to realize that what you're doing is bad, or that you're heading in the wrong direction, not so much to incentivize you, but to kind of, draw your attention to something.
So that definitely seems more on like the side of whatever the subjective human experience is of intentionality, because it doesn't seem like an AI would realize that that you're not really going to teach it a lesson unless the lesson is just based on like statistical probability of, if I do this, I'll get punished.
Yeah. So what's neat is that a lot of some of these models, these more what you're describing as like subjective intentionality models, we can start to actually implement those in machines, or implement those as programs now, as a kind of like theory of mind inference. So like we can actually kind of build systems that are doing Bayesian inference and thinking about, oh, what did this person mean? What is the likely meaning of this communicative action, either this demonstration or this punishment or reward? What did the human have in mind when they took that action? And so we can actually go beyond the kind of just pure statistical kind of like, oh, this like correlations or whatever, this happens when this happens, and actually think about, oh, like what was the meaning of this? Like what was the kind of intention behind this?
How does that play out when you're trying to look at it from an evolutionary perspective? Because there's going to be what maximizes like the cost benefit outcome of the individual, but then there's also like species level things that, so we could be selected for some behavior that maybe isn't fully optimal for an individual, but it would be for the species. So like sacrifice could be an example of that, sacrificing yourself for your family.
Yeah, absolutely. I mean, I think we actually shouldn't think of reward as it is subjectively experienced as directly mapping onto something like fitness, you know, because the like a reward system or any kind of cognitive or psychological system, neuropsychological system, it's selected for and it's subject to fitness, but it doesn't have to like map on directly to that. So, you know, you can like, for example, what you're saying, like I could find it extremely, you know, like I could be very drawn towards like sacrificing myself for the good of people I care about or something like that. And I guess that's a case where like it maps on to where like the feeling maps onto the fitness in a way. But so there's some interesting work thinking about, you know, how can like different reward functions be selected for through an evolutionary process. And so Fiery's done some work on this, kind of thinking about like retribution, particular types of retribution, and kind of whether it's something that is model based versus model free, like that can be selected for. The kind of particular mechanism that you're going to use in those cases will be selected for differentially. So yeah, I do think, you know, thinking about, or, you know, another possible example is something like hedonic treadmill. So like this tendency to want to have more, that could be an evolutionary, like, you know, an evolutionary adaptation that doesn't quite map onto the fitness, but, you know, getting used to, you know, it could be evolutionary adaptive to have a kind of mismatched reward function that's mismatched to the utility or the true fitness function. So I think, I don't know if that quite gets at what you're asking, but
you think value-based construal would map onto theory of mind as well? So you could imagine like hypothetically perfect theory of mind would require intense cognitive effort, but maybe you could just really try and spend a lot of time thinking about what this other person's experience is like and try and evaluate how any particular set of actions might not only make them like a very low resolution happy or upset at you, but go into the fine-grained details. So then you could imagine having like a value-based theory of mind. So you're only going to take into account the details that might actually matter for you.
Yeah, absolutely. So it's interesting that you mentioned that, because some of the motivation for me for looking into this question of value-guided construal was thinking about very hard planning problems, especially ones that arise in like social interactions. So like, so the teaching work that I mentioned before, in that work, like I said, we model people as kind of having being able to simulate other people's inferences or mental states in response to your actions. And that's a very hard problem, because there's a lot of possible beliefs that people could have, even in the simple domains that we were testing. And so we had to, you know, develop and apply these different approximation algorithms to even solve that. And it got me thinking, okay, well, people are somehow doing this in everyday life. How are we, you know, scaling? How are we able to like solve these very difficult problems? And yeah, this question, I think what you said, what you kind of described was kind of my working hypothesis, that like we are kind of forming simplified representations of other minds all the time. And these are, you know, sometimes geared towards our particular goals. Sometimes they're based on what we've learned. Yeah, and I think we can shift between different representations of how we think about other minds.
And another hypothesis here would be that your behavior might change depending on how close you are with a particular person, so how well you know them. Here's a like a real caricatured example. Let's say you had someone who you knew was, for whatever reason, very obsessed with colors, and there were a few colors that would make them very happy and a few that would make them very sad. So for example, maybe they love red apples, but they hate green apples. So if you're deciding to feed someone and you have apples lying around, for the most part, you might think, how many apples do I need for this amount of people? But then suddenly, if you're dealing with the color person, you're gonna think, okay, you're gonna have to take into account that extra bit of, do the colors of the apples matter? And so that would be an example where, like, the value-based construal, you would take into account the color of the apples, and then in most cases, maybe you could just ignore that piece of information.
Yeah, totally. That's a great example. I feel like someone should run that experiment. I think, yeah, it's like, right, when we represent other people, we need to be thinking about like what details of the world are they picking up on. And if we we care about how we're going to interact with that person, that's going to be reflected in what details we pick up on. And so, yeah, I think that makes a lot of sense to me.
Yeah, I guess the paradigm might be throwing a whole bunch of information about people at people, about hypothetical people, and then see which ones they actually use and which ones they remember. And presumably they'd only remember any that would be useful. I'm sure something like that has been done before, but.
Yeah. It reminds me a little bit of like, like the Linda problem in like behavioral economics, where like, it's like if you kind of present information in a certain way to people, they'll kind of assume that that's the most relevant information, and they kind of form kind of bias judgments. Like they use that as like a representativeness heuristic to respond, and like, aren't doing the full computation.
So during our last few minutes, what else is in the works for you, current or future research plans?
Yeah, so I think I'm very excited about the work that we've been doing on value-guided construal, and kind of thinking more about the role of representations in planning. So yeah, like I said, I think planning is really important for understanding what people are doing, people's behavior. And a kind of cool thing that I feel like the value-guided construal ideas have unlocked is thinking about, okay, how is attention, what is the role of attention and kind of building up representations of the world? What is the role of that in how we take actions? And so like the kind of the functional fixedness stuff I talked about earlier, I see that as a kind of very canonical, cool example of how people can be very like actively engaged in a planning process. They can be thinking really hard about a problem, but because they're not representing it right, because their attention is kind of locked in a certain way, they're unable to solve it in the best way. And so one kind of line of research that I'm hoping to publish soon is thinking about using this framework to model how people can learn kind of fixed kind of ways of seeing problems, similar to the functional fixedness thing, where they've kind of like locked into like using a particular type of construal, and then when they're given a new situation where that's not the best way to solve a problem, or the best way to solve a problem isn't given by that kind of type of construal, they get stuck. And so yeah, kind of thinking more about like these kinds of habits of thought type things is something that's very exciting.
Attention relate to that classic gorilla experiment. So people are given a task of counting how many times a basketball is passed between players, and a gorilla walks by in the background, and a majority of people don't even notice the gorilla because they're so focused on the ball. So do you think that relates to this research you're talking about?
Absolutely, that absolutely relates. I mean, actually, we were at one point we thought of running an experiment like that for the paper, but ended up not. But yeah, it's totally the exact same thing, that you are kind of you're representing the world in a certain way, and you're attending to certain things in a certain way. I mean, it is very value guided. It's task directed. You're told to count the number of basketball passes, I think, is in the original experiment. And so Yeah, so gorilla, not relevant, so you totally ignore it.
You know, I wonder of the people who did spot the gorilla, if they were secretly like losing interest in the task, if there would be a way to measure how focused someone was.
Yeah, that'd be really cool. So that's another thing I would like to do more work on, is thinking about these individual differences in attentional strategies, whether, yeah, and where they come from.
That's very exciting. Well, we covered so much ground. This was a true cognitive science conversation.
Yeah, computer science, philosophy, a little bit of everything.
Yeah, thank you so much for your time, Mark.
Yeah, thanks so much, Adam.
Take care.